Well, differentials. Here in this section, we want to talk about how is it possible to extract from a function from its derivative the small shifts in terms of x or in terms of y. We call the small shifting or the movement of x, we call those differentials. We could talk about the slight movement of x, or delta x, or the slight movement of y, delta y. And then we can approximate the delta x with dx, the differential, and we can approximate delta y with its differential, dy. And then from there we can talk about the so-called projected error, if it is known that if you are measuring certain quantities that there may be a measurement error in the tool that is being used. And so in calculation of an area or volume or whatever the formula may be, that area or that error, from the measurement of certain dimensions is exacerbated within the so-called formula. And so we talk there about the propagated error, the projected error that is typically allowed. How much error can this apparatus hold and yet still maintain its proper function? Whether it's the police radar detector and its so-called collaboration, or if it's an instrument in medical science that's being used, whether it's the x-ray machine, what's the propagated error? Even if it's in mathematical posters, if there's a certain segment of the population that's being extracted for a survey, for a poll result, what is the so-called allowance of the difference in the percentage, whether it's an alpha test, t-test, or whatever, what have you. The system works best if it understands that errors are possible and practical. So we start with the mathematical argument of where the differential actually comes from, which here it's easier to investigate it using the calculus. So the definition of the differentials, here we call dx and dy the differential. Obviously, if f prime of x is equal to dy over dx, if we can treat the ratio aspects as individual quantities, then we can extract dx and dy apart and thus look at dy equal f prime of x dx. Again, like we said in the beginning, delta x is a very small movement. Likewise, hopefully, the same should occur for delta y. Now, they have some formulas here. We will derive all of these as we work some problems, and we'll show you how that works. It's very straightforward. And error propagation as well. The propagated error is in the resulting function form. So here the change in y is what is to be examined or to be sought for. Delta x is the measurement error. And so it's interesting philosophically that within the exact value there's error. Well, that would be a good topic elsewhere in philosophy. The very interesting thing about mathematics is that the mathematics encompasses great philosophy, the philosophy of its day, and obviously we should consider the philosophy of our day as well. Exercise 7 to 10, this is number 8. Use the information to evaluate and compare delta y and dy. So we first compute delta y. delta y is this. Delta y is f of x plus delta x minus f of x. And you understand where that comes from. F prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x, and this is all over. The numerator is the change in y, and our denominator is the change in x, which is actually x plus delta x minus x. Well, obviously, your denominator just becomes delta x. This is said to be the so-called change in y with respect to the change in x. So if that be the case, they give us that delta x is being said to be equal, typically as approximation of dx. So here our delta y is f of x plus delta x. If x is negative 0.2, then x plus delta x, excuse me, it's just negative 2 plus 0.1, and so here this gives us negative 1.9. So this is f of negative 1.9 minus f of negative 2. So this delta y is, this is 6 minus 2 times negative 1.9 to be squared, just using y. Then minus, evaluate y at negative 2. So this is 6 minus 2 times negative 2 to be squared. Now on your calculator, when you calculate that, you get 0.78. Now, so what is dy? We want to compare delta y with dy. Well, we understand that f prime of x is set to be dy over dx. So this implies then that dy is f prime of x times dx. So let's see, f prime of x, this is y, so f prime of x is negative 4x. So this becomes negative 4x times delta x, or dx. So this is negative 4, x is negative 2, and dx is set to be approximated by delta x, 0.1, and that gives us 0.8. So delta y is 0.78, and y, and dy is 0.8. Very close. The most accurate value, as always in terms of using calculus, is the dy, and the approximation is the delta y. So delta y is said to approximate dy, and likewise delta x is said to be a very close approximation of dx. Here, find the differential dy for the given function. And so we have f of x is equal to the square root of 9 minus x squared. Now again, dy over dx is f prime of x. So this implies that dy, what you're looking for, is just its derivative times dx. So f prime of x is 1/2 times 9 minus x squared to the 1/2 minus 1, which is negative 1/2, times the derivative of the inside. Then we can clean this up. So f prime of x is negative x all over the square root of 9 minus x squared. So now you're looking for dy. So dy is the derivative times dx. So this is negative x over the square root of 9 minus x squared times dx. And the computer will mark it wrong if you leave off the dx, so you want to be very careful. Now we look at here the so-called propagated error. The measurements of the base of an altitude of a triangle are found to be 36 and 50 centimeters respectively. The possible error in each measurement is 0.25 centimeters. So here with the base, there's an error here of plus or minus 0.25, and then there's a possible error of plus or minus 0.25 for the altitude. What are they saying? They're actually giving you the so-called delta x, if you will, but here for the base, we'll call that delta b is plus or minus 0.25 centimeters, and then the delta h, the difference of the error for the height or the altitude, if you will. I just use h. This it. You get the same numbers. The base is given to be 36 centimeters, and the height is given as 50 centimeters. So use differentials to approximate the possible propagated error in computing the area of the triangle. Well, so the area of a triangle is 1/2 times the base times the height. So we found the so-called derivative. So this is dA over dx is equal to 1/2 times the derivative of b. So we just say this is db over dx times h plus 1/2 times b times the derivative of h, dh over dx. Multiplying through by the dx's, we have dA is equal to 1/2 times the differential of b times h plus 1/2 times b times dh. Now, they want us to use, for approximations, this delta b, which is the same as the delta h. So we're approximating with the dB and the dH. So we use the same numbers. So we're looking for here this so-called the propagated error. So we just put a plus or minus in front of that to give us that. So we have 1/2 times this plus or minus 0.25 times the height. The altitude was 50 centimeters plus 1/2 times the base, and that came out to be 36 centimeters. And then this is times plus or minus 0.25 for the difference for the so-called height. So we calculate that, and just want to be sure. So here we have plus or minus 10.75 centimeters squared for our so-called propagated error. Part B says approximate the percent error in computing the area of the triangle. What's the possibility, or what's the percentage of error that the area that you calculate is off a little bit, and how much is it off? So we find that percentage error. Well, this percent error is no more than the so-called propagated error divided by the actual area of the triangle. So here, this is okay. So the area is 1/2 times the base, 36 centimeters times the height. And so that is 900 centimeters squared. So we have this plus or minus 10.75 all over 900, and it gives us 0.01194, and of course times 100%. So we get 1.1 0.94%. Okay. That was for part A, then part B. Now, two more problems. Very neat ways to approximate an answer to a decimal. And this was really in the time that mathematicians did not have calculators like we do today. And so men like Abel and Dedekind and Cantor were instrumental in approximating certain numbers, certain radicals, if you will, without using a calculator. Well, they didn't have a calculator. And what they did, they were able to create these tables where you could just find the answer on a chart with squares, square roots, cube roots, and so on and so on, of very complex numbers. Well, let's see. What we need to understand here is that f of x plus delta x minus, you recall, f of x is said to be delta y. And dy is said to be approximated by this delta y. With f prime of x equal to dy over dx. This implies that delta y is f prime of x times dx. Now where does that come into play? So what we're going to do, we start here with this statement. And so this is f of x plus delta x minus f of x is being approximated by dy. Let's get a little bit rowdy. R-O-W, a D-Y. Hopefully I spelled that right. But kind of remember that in high school with the prep rally, which I didn't know what they were talking about because I was too busy trying to calculate some complex number. But anyway, I get it now after 30 some years. But okay, R-O-W, D-Y. I like the D-Y, the D-X better. So this dy is equal to f prime of x dx. We're going somewhere. So here, f of x plus delta x minus f of x is approximated by f prime of x dx. Most times you're going to be looking for a function evaluated at some x that you can find plus some shift that just messes up everything, like this 99.4, because I know the square root of 100 is 10, but I don't know by hand or head the square root of 99.4. So here's what we need. So f of x plus delta x can be approximated by f of x plus f prime of x delta x. That's important. Okay, so we're able to derive it. Derive what? Well, consider this, that x is equal to 100, because I know f of 100 is equal to the square root of 100, and that's equal to 10, something that I know, right? With that in mind, x plus delta x equals the 99.4. Well, if x is 100 plus delta x equal to 99.4, doesn't take rocket scientists. Ooh, my space is running out. Doesn't take rocket science to tell us that here delta x is 99.4 minus 100, or negative 0.6. Okay, so I want to find f of here. The x plus delta x is 99.4. I want to find that guy. So that's going to be approximated by f of x, which is f of 100, plus f prime of 100 times the delta x. Delta x is going to be approximated here. The dx is being approximated by delta x. I need more room. Why don't you move? I need more space. Well, why don't you move? Anyway. All right. So the only thing I need here in this equation is f prime of x. Well, f of x is the square root of x. That's the form for this problem. So its derivative f prime of x is 1/2 times x to the negative 1/2. Well, that's just 1 over 2 times the square root of x. So f of 99.4 is approximated by, let's go ahead and just put it in there now. This f of 100, that's the square root of 100. This is plus 1 over this f prime of 100, 2 times the square root of 100. It's a bad 100. You can't see it so well. And then this is times negative 0.6. This is 10 minus, or you can say plus, doesn't matter, 0.6 up top. And this is 2 times 10, or 20. And I must calculate that. Let's see. .97. Now on the calculator, you just plug in the square root of 99.4. The calculator gives you 9.96995. That's pretty good, pretty close approximation. Calculator being spot on, and then our approximated theory here using tangent line progression, and you get something very close. Now let me do this one quickly. Make sure we got it. The function that we're considering, f of x, is the cube root of x. Now if you think about here, the cube root of 26, which we don't know by hand, but we do know the cube root of 27, which is 3. So here we're set x to equal to 27, and x plus delta x should give us the 26. So if x is 27 plus delta x equal to 26, then obviously delta x is negative 1. Now we need that derivative. F prime of x is 1/3 times x to the 1/3 minus 1. We get negative 2/3. So that derivative is 1/3 times the cube root of x squared. So f of x plus delta x, that's what we're looking for, which is f of 26, and this is the cube root of 26. This guy is said to be approximated. We use the form that we got here. It never changes. So it's f of x plus f prime of x dx. F of x plus f prime of x dx. We got the dx. We got everything I think we need. So this cube root of 26 is approximated by, oh, the x is 27, right? So this is the cube root of 27 plus f prime of 27. That's the derivative is 1/3 times the cube root of 27 to be squared times negative 1, the dx. So this cube root, this is 3 minus 1 over, let's see here, the cube root of 27 is 3, right? To be squared, we get 9 times 3 is 27. And so on your calculator, you get 2.96296. Well, not on the calculator, just by hand. Is that right? 3 minus 1 divided by 27. 2.96296, yes. Now on the calculator, the cube root of 26 is 2. Look how close they are. 9625. Can't get no better than that, folks. Well, actually you can, but that's not for this class for right now. Let me stop there. Thank you.